Good afternoon, and thank you for coming back. I am Peter Duveen, your host, and today we're going to explore the motion of pendulums. Pendulums are a very old study, and Galileo paid particular attention to them, and there's a famous story noting that Galileo said that when a light swings back and forth in the church, it doesn't seem to matter how big its amplitude or breadth of motion is, it always has the same period. Well, it turned out that later investigators found that that was not quite true. There is a difference depending upon the amplitude. The amplitude does affect the period. And so you can see that people were very interested in exploring the motion of a pendulum. Particularly Christian Huygens, the Dutchman, explored this in conjunction with the manufacture of his pendulum clocks. And he found that it is not really a circular arc that has the perfect period that is not dependent on the amplitude. It's a different type of arc called a cycloid, which is a bit different. It's actually the curve that is made if you take a point on a wheel, and if you follow that point as the wheel proceeds, that actually turns out to be a cycloid. Christian Huygens found out that it is actually the cycloid that if something is constrained to move in the shape of a cycloid and not a circular arc, that the period will be independent of the amplitude. So that was one problem that Christian Huygens solved, and there were a number of other problems, but today we're going to try and make it simple, and we're going to take an interesting tack. As it turned out, this seemingly simple motion is not so simple, and it actually takes some rather advanced mathematics to approach it. But if I alter this motion just slightly, and I create what is called a circular pendulum, it turns out that all of these mathematical difficulties literally evaporate into thin air. So what we're going to do is simply derive or model the motion of a circular pendulum, and from there we will be able to solve this type of motion a bit more simply to some extent. And we'll be able to solve many other problems simply by beginning with the circular pendulum. So that is what we're going to try and do today. We're going to take our first steps in this session. What I want to do is first draw a model of what's going on. There's the vertical axis, more or less, and here is our circular pendulum with the weight hanging on it of mass m. Why not put that in there? And this is going in a kind of circular fashion. I'm trying to indicate it in 3 dimensions in a way. Around this circle, if we want to see what the circle looks like, it looks something like this head-on if you were to look down. There's the circle, and there's the bob right there, and it's traveling around. Let's make it travel around in this direction, although it's really not going to matter. So, what can we say about this? Well, let's look at the forces that are acting on this mass here. First of all, there is its weight. So I'm going to put a line and we'll call that mg. I'll put a little arrow. I don't want to put mg yet. I just want to put w. We'll put mg later. Okay, w. And then there must be some force which is preventing this weight from falling down, or prevent it from leaving this plane of action, because actually it is it is revolving around an axis in a plane, and you'll notice that it doesn't leave the plane, so we can imagine that there are no forces acting perpendicular, no net forces acting perpendicular to the plane on this particular object. And that's going to help us. We also have the tension. So these are the two. The tension is the tension of this string, which is holding it up. So those are the forces that we know are acting, and I don't see any others except perhaps air resistance. And we're not going to take that into consideration. We're going to ignore that for the moment. Now, if we look at the tension, I'd like to look at the tension in a separate diagram. Here is tension. I draw a little arrow there. I'm going to break it up into two component forces, which, if acting together, would have the same effect as the one single tension. And we do that by using the parallelogram law of forces. It's a little bit crooked, but I'm going to call this component T sub y, and then this component acting like that, T sub x. So, this is a rather important and interesting diagram here, and this angle here, theta, okay? That's interesting angle there, and yes, you'll notice that that angle is the same as which angle? This angle here. So, those angles are the same. And what we have here, this of course is a right angle. We've drawn it as such, and so we really have, put these little dotted lines. Here we have two similar triangles, because if you remember from geometry, if it's a right triangle and we have one of the other angles, if two of the angles of two triangles are equal, the measures of those angles, then we have congruent triangles as they're the same shape. So therefore the ratios of their respective sides are going to be equal. And I'm going to use that right now. First of all, I want us to note that T sub y is perfectly balanced by W, because there's no motion outside of the plane, therefore there must be no forces which are creating, no net forces to create an acceleration that would cause our little bob to move. Then there's T sub x. And T sub x is an unbalanced force, and it is creating a circular motion around this axis, or seen from the perspective looking downward, you can see that our little mass is moving in a circle. And so T sub x is an unbalanced force, and it is creating an acceleration, and that acceleration which causes our body to move in a circle. So we have two equations really. One is T sub y minus W equals 0. And as a little aside, since all things accelerate at the surface of the Earth, roughly at a particular place on the Earth, with the same acceleration, which we generally note as g, we often like to replace the weight by the mass of the object times the acceleration which is produced, which is g. So therefore, we say T sub y is equal to the mass of our little body times the gravitational, oops, I jumped ahead a little bit. Jumped ahead, it's T sub y minus mg is equal to 0. The mass times the gravitational acceleration equal to the weight. And so I rewrite that finally as T sub y is equal to mg. My other equation will employ the previous equation that we had arrived at for acceleration in uniform motion in a circle. So that acceleration, I'm going to write it down here, A is equal to v squared over r, where r is the radius of the circle. We're going to put r here as well. R is the radius of the circle, and v is the velocity of our little mass there. So if I wanted the force, then it's going to be the mass times the acceleration. If I want the force that is pulling this in, then that's simply t sub x. So I'm going to write here t sub x is that unbalanced force is equal to the mass times velocity squared over r. Now, we have these two equations, and we're going to combine them so that all that we have in our equations are observables. But right now, I'd like to leave our progress at this, and in part 2 of our video presentation, we promise to come back and use these equations to actually provide something useful for us. Thank you.